Hello and welcome to the next lesson of Unit 7. We're going to talk about related rates. When we talk about related rates, these are basically application problems that go with implicit differentiation. So just to review, we are not going to abandon our other derivative rules. We still will use basic derivative rules when we see polynomial form. If we see a product or a quotient, we will have to perform that rule, and chain rule kicks in not only when you have a composition of functions, but obviously when you do implicit differentiation as well. So the first thing I'm going to do is I'm going to go to this link and just give you, again, as I always do, the why. Why are we learning about related rates? So I've been using this website for a while. I think some of the animation, I think it's starting to get old. I probably need to look at something else a little bit more up to date. But I'm going to click on a few of these and just kind of explain what the idea of related rates is about. All right, so I'm going to click on the conical sand pile because I grew up in Cowtown and we saw all kinds of silos, and my dad worked in the fats and oils industry. And if you think that this video is boring, I could, pull up the guy and he could tell you everything you can do with a soybean or corn. Nevertheless, I guess that's why I always think of that analogy whenever I see this problem every year. So here's what's going on. It's really any granular substance. So if you're moving anything up and when it comes down, and I think we did an angle of repose problem at one point when we did trig sometime this year, you can relate a variety of things going on with this cone. The height's changing, the radius is changing, the diameter is changing, the volume is changing. Everything is changing, but they're not changing the same. It's not like I'm saying the height is growing 1 foot per minute and so is the volume in terms of, so we can't even measure a linear measurement with the cubic. But here's what we can say. We can say that maybe in this particular example that the height and the radius, that they're changing, but the rates of change are just related with respect to time. And I can't write on this because it's the internet. I can only write if I'm on that other program. But we're talking about relating two or more geometrical kind of things that are changing with respect to time. So another classic related rates problem is a sliding ladder problem. If you look at the ladder, it's a 10-foot ladder and it's fixed. Can't change that, and we're not talking about the ones that you can make bigger and smaller. It's a 10-foot ladder, and what has to happen is it always has to remain within Pythagorean theorem when it's leaning against the wall. So the top of the ladder is falling down the wall, the foot is falling away from the wall, but they're not falling at the same rate. Think about a 3, 4, 5 triangle. If you had a 5-foot ladder that was 3 feet on the wall and 4 feet away from the base of the wall, if they both went down 1 foot per second, well, if I had a 2 and then a 5 and then a 5 triangle, that doesn't work. It doesn't stay in Pythagorean theorem. So the top of the ladder and the bottom of the ladder, they are falling at different rates, but those rates are related over time. Here's another one that I sometimes like to do is the oil spills. Historically, this is probably before your time, but if you ever want to look up on the internet about the Exxon Valdez, which was a tanker that I believe was in the Northern Pacific, and it dumped a bunch of oil and did a lot of damage to our environment. And I'm not going to sit here and say that the oil spill at all was remotely this nice, beautiful ellipse. But the idea is that, they do kind of go out in a circular pattern. And when they want to determine maybe like how far reaching the damage is, they're going to look at the rates of change. So if I wanted to look at the rate of change of the semi-minor axis of that ellipse, or semi-major axis of the ellipse versus, let's say, the circumference of the ellipse, you guys, they're not increasing at the same rate, but the rates at which they are increasing are related over time. Let's do one more, something a little bit more fun. Let's do a baseball, and we will do a baseball problem in our notes. That will come up in the next video. So in this example, I know I've got some baseball players out there, and we're all, at this point hoping that we'll see some type of season this year. But if you've got a runner coming off first base, it makes a right triangle with home plate where first base is your 90-degree angle. And the runner obviously has a rate of change. He's got some type of speed. And then the rate of change of its distance from home plate is changing. But they're not changing at the same rate, but they are related over time. So I'm hoping that this little background just kind of gives you an idea of where we're headed. Here's the good news. There are some specific mechanics that I'm going to teach you that are related to these problems. Did you see what I did there? Related to these problems? Okay, it wasn't really funny, but you guys, it's like 9:51 in the evening and, getting tired. Okay, so here we go. I am going to show you how we're ending our problems in the next video. In the next video, you will be given a word problem. Yes, words. I'm going to break it down for you. Don't get nervous about that. In the word problem, you will have to come up with an equation. In this example, I'm giving you one. In the word problem, you are going to have to extract given information. So when you look at problem A, I am giving you given information. We're going to struggle with that in the next video. So what I need you to do in this very short assignment that follows this video is to practice mechanics. You are practicing algebra. You are practicing a process. So I know that these are going to seem pointless. This is my 6th year teaching this. Trust me, if you can get these mechanics now, when we do the application problems tomorrow, we can fight through the how do we get the equation and how do we get the givens, and then you're going to know exactly what to do. Here's the process. I can give you a recipe. Step 1. Okay, in this problem, I'm going to go ahead and I'm going to distribute y equals 2x squared minus 6x. I think it's just going to make my presentation easier. All right, here is what changes significantly from the previous lesson. In the previous lesson, whenever we had an x variable, we didn't do anything. Ooh, isn't that interesting what that did? We didn't do anything. We just differentiated as normal. When you had a y, we had to include a dy dx factor due to chain rule. But friends, now we are differentiating with respect to time. So when I differentiate the y variable, it is 1 by power rule, but then the inside function isn't dy dx anymore. We're differentiating with respect to time, so it is a dy dt. When I differentiate 2x squared, by power rule, basic differentiation rules, we get 4x. But I'm not differentiating with respect to the independent variable x. I am going to differentiate with respect to time because that's how it's related to the rate of change of y. When I differentiate negative 6x, again, it'll be a minus 6 by power rule, but I have to include a dx dt factor due to chain rule. That is the end of your calculus. The next step is I'm going to go to problem A. They want me to find dy dt. This is what they want me to find. Then I'm going to rewrite the 4. And then instead of the x, they told me x was 3. So I'm going to substitute that value. Next, they have given me that the rate of change of x with respect to time is 2. And right now it's a pointless problem, so I don't know what that rate is. If it's 2, feet per second, whatever, centimeters per hour, we don't know because this is a pointless problem. All right, then I have a minus 6 and then another dx dt. So pointless problem, but the rate of change of y with respect to time, 4 times 3 times 2 gives me 24 minus 12 is 12, whatever the rate of units are. So again, I know it's a pointless problem, but this is the recipe. First, we differentiated with respect to time. Then we substituted in our values and we solved. B is still going to use our differentiated with respect to time equation. I just changed it up, and instead of asking you what is dy dt, I've asked you what is dx dt. So this time I can substitute in a value for dy dt. dy dt as given information is 2. They told me x was 1, but I don't know dx dt. That's what I have to find. And this is just a matter of some algebra. So this is 2, and I have 4 dx dt's minus 2 dx dt's. So that would give me a total of negative 2 dx dt's. So when I divide by negative 2, this means, again, it's a pointless problem, but the rate of change of x with respect to time would be negative 1 and whatever those units would be. Let's do one more. All right, I was told that dx dt is 2 centimeters per second, and they want you to find dy dt when x is equal to negative 2, 0, and 2. So kind of a three-parter. The good news is I only have to differentiate once. You can choose to do quotient rule on this, and you might look at it and you're like, but why am I, this is a related rate problem. So I have to differentiate implicitly with respect to time, even though this is an explicit function. I'm going to do an algebra rewrite step. I'm going to choose to write this as 1 plus x squared to the negative first, so that when I differentiate with respect to time, I get dy dt is equal to, and you know what I'm going to do? Let me move that over. I think I'm going to run out of space. Oh, let's get rid of that. You know what? It's probably just easier if I just erase. Let me just rewrite it. Sorry, guys. Note to self, maybe wait until like the morning to do this. Okay, here we go. So the derivative of y with respect to time is dy dt. Then when I differentiate the right side, I do have to use chain rule. I'm going to have a negative 1, 1 plus x squared to the negative 2. That's the derivative of the outside, times the inside, which is 2x, but then chain rule again, times dx dt. So when I write that all nice and pretty, dy dt is equal to, I have a negative and a 2x that live on top. I'm going to have a 1 plus x squared to the second power on bottom, dx dt. So let me go ahead and erase that so I can give a little bit more space. And let's cut this. Oh, I don't want to do that. Let's do undo. All right, and let's make that a little bit smaller. There we go. Okay. I think I have what I want. All right, here we go. So let's answer the question. The question wants us to find dy dt. And the first case is when x is negative 2. So that means I'm going to have negative 2 times negative 2 all over 1 plus negative 2, the quantity squared, and then my dx dt is 2. All right, well, this is going to give me a positive 4 on top. Negative 2 squared is 5 plus 1 is 5. I'm going to get a 25 on bottom times 2. So this gives me 8/25, and they did give me a rate, so this would be centimeters per second. All right, let's do part B. Part B is going to be dy dt, and this should be nice. Where I see these negative 2's, what are we putting in there? We're putting in zeros. So when I put in 0, that means the numerator is 0. I don't need to do any of the other work. I get 0 centimeters per second. And then here's what's nice for part 3. On part 3, when I want to find dy dt, well, it's that exact same work, except that negative 2 is now a positive 2. So that's going to give me a negative 4 up top. I'm still going to get a 25 on bottom times 2, and that gives me a negative 8/25 centimeters per second. All right, friends, please do the following. It's not very long. It is 1 to 7 odd. Please, please, please do this so that you can get those mechanics down, and I will join you in the second video. Cheers.